in Jacobian algebras via punctured skein relation.
Well, hey everyone, thanks to the organizers for inviting me, and thanks for the chair and moderator people who work so hard in this conference. So there's a bit of an overlap with the previous talk, and also it's good that the previous talk exists because it shows how punctures make everything more complicated always. So, okay, I'm going to start. Also tell me if it is big enough. First, by speaking a bit about cluster categories from market surfaces, just to know the main ingredients. Then I want to give an example, which is also for me a motivation. And by the way, I'm going to use this to settle some notation. Then I go to the result. About non-split triangles and extensions in presence of one puncture. So let's start. First, as before, S is a compact, say, oriented Riemann surface. It has a finite number of disks removed. Maybe. And M is a set of market points. So some of them might be on the boundary, and some of them might be on the interior of S, and that's what we call punctures. We also ask that each boundary has at least one marked point. And then in there we say an arc is an isotopic class of arcs, of curves, say that start in a marked point and a marked point. These arcs can have a tag. It can be not plain. Also, other curves may appear in your surface. For example, you may have something like this, and this is not an arc, but it's a generalized arc. This may happen. You have a boundary, and you have this, but we don't consider this. But they may appear. Also, don't do this at home. We don't want you to do that. Okay, so in this world, I will call it, say, a crossing number. For two, say we're considering tagged arcs. For two tagged arcs or generalized arcs, something that will be denoted like this. And it's essentially the number of crossings in minimal position for alpha and beta that you see in the interior of the surface. But, okay, I want you also to remember the tag rule of compatibility that says, say you have some mark point here, one mark point here, and a puncture, and you have this one, and they may have a tag. Since we're going to stay planar, I'm going to say this, that basically think that if they come from different points and they have different tags, they have crossing at the puncture. It's important that we say at the puncture. And maybe if we have something like this, but they came from the same marking point, well, they don't cross. What to say? Okay, if I want to keep the notation or the words of the previous talk, I was going to say a multicore, but I say a diagram. Is a finite set of generalized arcs. All drawn in the same surface. And this corresponds to multiplication in the cluster algebra set, and corresponds to direct sum in the cluster category set. And finally, obvious. triangulation is maximal set of non-intersecting tag arcs. And I don't want to forget, there's a lot of references about this. I'm going to mention just a few of them. Caldera-Chaperon Schiffer for type A, Schiffer for type D, and then the definition of cluster algebras from surfaces from Shapiron-Thurston, talking about multicurves and multiplying them. It also appeared in their previous talk. Several things can be named here. So this is our setting. This is just an overview. It's a very rough overview of the setting, but we know the setting now. And I go now for an example. I'm going to take S and M to be a torus with one boundary. Two market points. At the boundary and one puncture. And I'm going to post the triangulation. So some people may not like this picture, but I like it. There you go. There's a triangulation on a torus. Do you believe me? I hope you do. Okay, this is the arc 2, this is the arc 1, 2, 3, 4, 5, 6, 7. This is a puncture. 8. They're all triangles. I hope that they are. Okay, and maybe to finish the overview, say that you can define the cluster category associated to S and M. Again, references as before, maybe Bruce Lechang, Q so for the puncture case, in which an arc corresponds to a rigid object, in which the triangulation corresponds to a cluster tilting object, in which the intersection number corresponds to the dimension vector space. And then that even more references, but I can mention Assen, Rostle, Cabo-Dochodon, Salomon Dominguez, Daniela Bardini, who is with us now. And they can consider a quiver with potential. Associated to the triangulation on the surface, and you can build the Jacobian algebra for it. And in this setting, I want to say, okay, if you see, here's called a diagram in your surface. I want you to say this is a bunch of arcs or generalized arcs. Then I want you to consider direct sum of objects in the cluster category. Now for the example, I want to go and cite now new citation, Chanaki Troll, and say that they studied triangles and extensions in the non-punctured case. For that, we need the notion of a usual skein relation. Say this is alpha, this is beta, this is the cross ones. And you want to convert this into this one and this one. And you know this is a valid equation in the cluster algebra. You know that this multiplication is equal to this plus this. And here I want to set a notation, and I want to say that if you walk through alpha and you find the intersection with beta, and you decide instead of following alpha going to your left, then we are going to do this multicurve. And this one corresponds to this one. And these are multicurves. And okay. Yes. Yes, if this orientation is the one that works good for the orientation that I'm going to write here in such a way that everything works. Yeah, so what you will call plus, then you can change your convention, of course. But what you call plus is will be revealed like now. Like you have to settle your convention and follow it. No, no, as like this goes that way. No, 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 they are not oriented. They're asking if this has an orientation as like this, like starts in A and ends in B, and no. But there is a matter of orientation that will show up here, like how do you choose to do your triangulation? But no, this arc is unoriented. All of them were unoriented. So I have a triangulated surface here. And I could think of the Jacobian algebra corresponding to this, but say I have two arcs not in the triangulation, say alpha beta, and they cross once. So according to the theorem, can I control? Well, first, if you see two generalized arcs that such that the number is 1, then you know that there are non-split triangles of the form like this. And of course, this is symmetric. You can do the other way around. And also, that's the first part. The second part is that given a triangulation, you can think of and say that alpha and beta are not part of it. Then you can say that there's a module, a string module associated to alpha and a string module associated to beta in your Jacobian algebra. And the modules may cross in a module in an arrow or in a tricycle. And these two will give you the result that exists a short exact sequence, while this one will tell you that no, there's no short exact sequence. And I could give you the definition of modules crossing in an arrow, in a cycle, and more. But through this, I don't remember them. And I want you to not remember them either, because I don't want you to think of that. I want you to think that the extension will exist as long as the dimension of the K vector space is preserved. And that's it. That's the sentence you want to remember. Okay. I was going to give you an example here, but now I want to go for the one puncture case. And okay, I want to address what kind of extensions may show up when you have a topological thing that has one puncture in the middle. And well, it may happen that you have something like very similar as before. But maybe one of your things was a puncture. One of your market points was a puncture, and you have to like keep thinking the same as before. And this is also an equation in cluster algebra. It may happen that you have the puncture and something comes and they cross at the puncture and say this is alpha and this is beta, to be the other way around. And yeah, I want you to do the same. You say, I go through alpha and I find the intersection point and I want to go around it left. So I want to do this. You can do it. And then again, this is this and this is this. And the most complicated thing that may happen is that this is in fact 2, because what happens is that you have the puncture in the middle and you have something surrounded like this or something like this. And for that, I want you to consider this. Plus mirror of the other way around, the other 4. So this is just and here you should consider also this. And this is a nice equation because I like remembering like this. This is okay. This 2-dimensional intersection. So this is a 2 here. 2-dimensional intersection is equal to, I lose 1-dimensional intersection here. There's a 1 crossing here. I keep 1. This is a plus. Here I keep 1. This is a plus. Here I keep 1. This is a plus. Here I lose it. This is a minus. This is a valid equation in cluster algebras. You find it by skein relations, of course. And the things that show up here are all the possible multichords that give you the middle term for a triangle that arises from this topological picture. All of them. So if you go here, say, and the theorem is, of course, 2 minutes. A for arcs alpha and beta as above. There are non-strict triangles. In the cluster category. Where CI is one of the ones listed here. And moreover, given a triangulation, then the triangle becomes a non-split sequence. If and only if the number of crossings of alpha union and beta with T is the same as the number of crossings of your multicore with T. Okay, I was going to do one there, but okay, I'm done. This one?
Okay, so let's thank Anna first. Any questions?
What? What is? As here. In these topological settings, like in the previous one, as in Kanaki's role, or like this, or like this, or like this. Yes. Or whatever that you can draw in a way that refers to that. I was going to do an example here, a bit strange one that reduces to that.
On the top line, one tag on one of the arcs on the left, and no tag on the right.
Yeah, because I'm considering only one puncture. So you can consider no tags or one puncture where you have a tag or no. This equation is always true in cluster algebras. You can have a tag here and also a tag here, but yeah. Yes. You preserve it, of course. You preserve it. I forgot. You preserve it. I would love to. I would. Do I have a category? Okay, I was expecting you to ask this, or you. So the question is if this is a categorical equation. This is a categorical. Here you have the mirror thing. You have almost the same as the other way around. So it's plus, 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 minus. And it's nice. It's a nice way for me to remember the formula. But if it arises from a generalized cluster character formula, is something that I don't know, but I would like to know. I think the closest thing I've read about this is cluster characters 2 by Palou, but I don't remember a minus sign anywhere. So maybe it's I don't know. I like it. So if you know what you're doing, you easily remember what to put there, for sure. But I don't know. I would like to know if there is one.
D3 still has a crossing with it, so if you solve that, but that actually cancels D4.
Yeah, this. Yeah, of course. So this all follows from key relations formula that you can follow, and this is the kind of computations you do.
With that in mind, the way of doing it, D4 is there. Does D4 actually appear in the triangle?
It appears in most of the generic one.
Yes, this is the special, this is the generic.
Yeah, he told us the answer was
Minus one is the other characteristic.
I just found a nice formula that keep them all. I want them to all of there. And I have a nice way to remember the sign of each one of them. But like if this is suitable for some cluster character interpretation or something like that, that says, haha, that's how, that's why. I don't know.
No, but you try and take the online
Yes, there's a, but they can't be negative. Yes. So the problem is that if I want to use a, so I think what Matt is trying to say is, so there's formulas for this, like you want to put the dimension of the intersection here and something that has the next positive, and there's an Euler formula, but everything that appears is positive. Maybe? No? They're Euler characteristics, they can be negative. Okay, so maybe this is the translation of one way to interpret one of these formulas.
Greg, maybe it's easier if you just say.
Oh, hi. So I was kind of curious whether the representation perspective suggests any particularly nice way to quantize the punctured skein algebra to stick Q parameters in there.
So I don't know. So I have no idea about quantizing this. But so the thing is, I got my inspiration to do this was reading a quantum cluster paper where they use, there's a lot of these formulas, of course, but of course, when they don't draw the things on the same plane, they stack on top of each other, and there's a Q. But that's where I took this notation from. I understood what they were doing, but I basically used their knowledge in my advantage. But I don't know much about this. So this formula should be like this. The notch thing is on top of the other one. Yes, maybe you can extract some formula from it.
-5 is Q -2.
Q minus 2. You can follow up all these formulas in the quantum case, sure.
Okay, so let's thank Anna again.